AI does not live in the cloud. It lives on a power bill. Every chatbot answer, every model training run, every AI image, every video generator, every recommendation feed that feels weightless on your screen eventually turns into heat inside a building full of servers. And that building needs electricity, not vibes, not magic, not a cloud floating above the economy. Electricity. AI Cloud Ball says, I am digital. Utility Ball looks at the meter and says, then why is my grid sweating? This is the hidden part of the AI race. Companies are not only fighting for chips, they are fighting for megawatts, grid connections, power plants, transformers, cooling systems, and the right to plug in before somebody else does. So the real question is not just who builds the smartest AI, it is who gets the power. And after that comes the question nobody likes: who pays for it? Start with the word everyone uses: cloud. Cloud sounds clean. Cloud sounds invisible. Cloud sounds like your question flies into the sky, gets answered by a genius mist, and comes back as a paragraph. But the cloud is not a place in the sky. It is a building, usually a very large building. Inside are rows of servers, chips, cables, fans, backup systems, cooling equipment, security, and a utility meter that does not care how futuristic the marketing is. When you ask an AI system to write, draw, search, summarize, code, or generate video, computation happens somewhere. Computation uses electricity. Electricity becomes heat. Heat has to be removed. Removing heat uses more electricity. So a data center is not just a computer warehouse. It is a machine that turns electricity into computation and heat. Ratepayer Ball says, wait, I thought AI was just software. Utility Ball says, software is what happens after the power arrives. This is why energy agencies are watching AI so closely. The International Energy Agency estimates that data centers used about 415 terawatt-hours of electricity in 2024. That was around 1.5% of global electricity consumption. That number can sound small, and globally it is still a small share. But small global shares can become huge local problems. The same source says the United States accounted for about 45% of global data center electricity consumption in 2024. China followed with about 25%. Europe was around 15%. Now, think like a grid operator, not like a phone user. If a giant new data center wants to connect in a place where the grid already has spare capacity, maybe it is manageable. If 10 giant data centers all want to connect near the same cheap land, fiber lines, tax incentives, and existing tech cluster, suddenly the local grid is not asking, what percent of the world is this? It is asking, can this substation survive Tuesday? AI Cloud Ball points to a chart and says, but I am only a tiny part of global demand. Town Ball points to a transformer and says, you are not tiny here. That is the first important distinction. The AI power story is not just about the global number, it is about speed and concentration. For decades, many advanced economies planned around slow electricity demand growth. Then AI arrived on top of cloud computing, streaming, electrification, factories, air conditioning, and everything else trying to plug in. The IEA projects data center electricity consumption could more than double to around 945 terawatt-hours by 2030 in its base case. That is not AI alone, but AI is one of the major drivers pushing data center demand upward. In the United States, the Department of Energy and Lawrence Berkeley National Laboratory reported that data centers consumed about 4.4% of total United States electricity in 2023. They also reported that United States data center electricity use rose from 58 terawatt-hours in 2014 to 176 terawatt-hours in 2023, with estimates of 325 to 580 terawatt-hours by 2028. Utility Ball hears those numbers and starts ordering coffee by the barrel. Because building a data center is not like plugging in a toaster. First, the company needs land, then fiber, then water or cooling options, then permits, then equipment, then a power agreement. Then the grid operator has to ask if the system can actually handle the load. And that is where the bottleneck moves. The internet talks about GPUs. The power sector talks about interconnection. A data center can buy chips faster than a region can build transmission lines. It can announce a project faster than a transformer can be manufactured. It can promise an AI future faster than a utility can upgrade a substation. The IEA warns that if grid risks are not addressed, around 20% of planned data center projects could be at risk of delay. It also notes that building new transmission lines in advanced economies can take 4 to 8 years, and that wait times for critical components like transformers and cables have doubled in the past 3 years. AI Cloudball says, I need power next year. Transformer Box says, take a number. This is where the story stops being a tech story and becomes an infrastructure story. A data center does not just need electricity somewhere in the country, it needs electricity at a specific location at a specific time, with enough transmission capacity, enough local distribution capacity, enough backup, enough cooling, and enough reliability that the servers do not go dark. That is why utilities and regulators are now asking questions that sound boring but decide the future. If a giant customer needs a bigger substation, who pays? If a new transmission line is built partly because of data center load, who pays? If a power plant stays open, starts up, or gets built to serve new demand, who pays? If the costs are spread across all customers, does the household bill rise? If the data center pays all upgrade costs, does the project move somewhere else? If the company promises to reduce usage during grid stress, should it get connected faster? Regulator Ball opens a folder and says, welcome to the least glamorous part of the AI revolution. In the United States, FERC has an official proceeding about large loads connecting to the interstate transmission system. Large loads include data centers and manufacturing facilities. The questions include how to connect them in a timely, orderly, reliable, and non-discriminatory way, and whether large customers should pay for grid upgrades needed for their interconnection. That sentence is dry. It is also the whole video. Because the future of AI may be decided inside rooms where people argue about cost allocation. Now add the power supply problem. Where does the electricity come from? The simple answer people want is usually one word: gas, solar, nuclear, wind, coal, geothermal. The real answer is uglier and more interesting. All of the above, depending on the place, the hour, the contract, the grid, and the politics. Renewables can be built quickly in many places, but they need transmission, storage, and balancing. Gas plants can provide dispatchable power, but turbines and pipelines have their own lead times, costs, and emissions fights. Nuclear can provide constant power, but new projects are slow and expensive, while advanced reactors are still trying to prove themselves at scale. Geothermal sounds perfect in some locations and hard in others. Batteries help with timing, but they do not erase the need for enough generation. Power Plant Ball says, pick me. Solar Ball says, pick me. Nuclear Ball says, pick me, but start paperwork yesterday. Utility Ball says, I need all of you to stop yelling and give me a reliable hourly plan. This is why AI is turning electricity into industrial policy. If a country can offer cheap, reliable, fast-to-connect power, it can attract data centers, cloud regions, AI labs, chip-adjacent industries, and the jobs and leverage that come with them. If it cannot, the compute goes somewhere else. That does not mean every data center is good for every community. A local town may see tax revenue and jobs, but also water concerns, noise, land use fights, grid upgrades, and fear that ordinary customers will subsidize a massive private load. Town Ball says, is this economic development, or am I buying somebody else's extension cord? That is the correct question. Because a data center can be a good deal or a bad deal depending on the contract. If the company pays for upgrades, funds new clean power, uses flexible demand, and helps strengthen the local grid, the project can be part of a bigger infrastructure build-out. If the costs are socialized while the benefits are private, the politics can turn ugly fast. So, who pays is not a slogan, it is the mechanism. The tech company wants power quickly, the utility wants reliability, the regulator wants fairness, the politician wants investment, the community wants jobs without surprise bills. The ratepayer wants the lights on and the bill down, and the AI model just wants more compute. This is also why the AI electricity debate gets so emotional. Both sides can tell a true story. The optimist says data centers can finance new power, improve efficiency, anchor advanced nuclear or geothermal projects, and help modernize the grid. The skeptic says giant private loads can strain local systems, delay other projects, raise costs, and lock in rushed energy decisions. Both can be right in different places. The real dividing line is planning. PJM, one of the major United States grid operators, has warned of significant long-term load growth. Its 2026 forecast expects summer peak demand to climb by about 85,000 megawatts over 15 years, and it specifically identifies growth in data center load across multiple zones. Again, that does not mean the whole grid is doomed. It means the old assumption that demand barely grows is over in some regions. Utility Ball looks at the old forecast and says, this was for a sleepy grid. AI Cloud Ball rolls in with a warehouse full of servers and says, I brought friends. So the AI race has two layers. Layer 1 is the famous layer: chips, models, data, talent, apps, capital. Layer 2 is the physical layer: electricity, land, cooling, transformers, transmission, generation, permits, regulators, and local politics. The first layer gets the headlines. The second layer decides whether the first one can turn on. And this changes how you should read AI news. When a company announces a massive data center campus, do not only ask how many GPUs it will have. Ask where the power comes from. Ask how fast it can connect. Ask what grid upgrades are required. Ask whether the project can reduce load during emergencies. Ask who pays for the transformer, the substation, the transmission, the backup, and the risk. Because the cloud is not floating above the economy, it is plugged into it. And if enough companies are racing to plug in at once, the bottleneck is not only silicon, it is sockets. AI Cloud Ball says, so I am not weightless. Utility Ball hands over the bill and says, nobody is weightless after the meter starts spinning. That is the power bill behind AI. The next AI race is not only about who builds the smartest model, it is about who can deliver the electricity, who gets connected first, and who is left holding the bill.